Now we're going to talk for a little bit about adaptive area CFARs. When I described the pulse Doppler system, the moving target detector, you remember that there is a range for each range azimuth Doppler cell. There's a linear CFAR technique where a mean level of the background is measured by taking and looking at the mean in range, 7 or 8 cells on either side of the target of interest, and leaving a gap between the target and the cells you leave. You measure the mean level from, dividing by the total number of cells, and that gives you, and multiplying it by a constant, and that will give you a good threshold to measure adaptably every scan for every range azimuth Doppler cell, how far a given range azimuth Doppler cell is above the mean background in that local area. And that works very effectively on mitigating any diffuse false alarms, any false alarms due to diffuse clutter in the range azimuth Doppler domain nearby. But one thing that was noticed when the moving target detector, or would be noticed with any pulse Doppler ground-based system, in this case an ASR 8 equipped with the second generation moving target detector, at a site in Burlington, Vermont, particularly chosen because it was near the Green Mountains, which as you're at the airport, you could look up and see just a row of mountains about 12 miles away from you. We wanted to have a place where there was very large ground clutter. And in fact, some of that ground clutter exceeded the dynamic range of the A to D converters that we had and broke through as ground clutter breakthrough. But there also was a significant amount of birds up in that area, and it was tested over a long period of time, so we saw bird migrations. And we were able to stress quite nicely the capabilities of the second generation moving target detector. That effort was led by the late Dave Karp and John Anderson, and is documented in reference 7 quite well. What they did, and I think looking on that was done 25 to 30 years ago, is they developed a second generation of thresholding that said, we understand that as you look at this graph on the right, which is the density of targets in 2 dB bins, and as a function of target cross-section, well, here is the point where you have a Piper Cherokee nose on, and up this way, well, you'd want to see these guys. But you'd also see all these other point targets which passed the thresholds that was set up by the ASR 8 at Burlington, Vermont. And area CFAR techniques were looked into to mitigate this problem on the second generation MTD. And I say that because there have been several different major efforts culminating in the what was the specification of the ASR 9, which is in place today, as what the FAA calls its gold standard in radar, airport surveillance radar technology. It is a very sophisticated area CFAR technique. And that area CFAR technique, not the best one, but an example of one such technique on that road to progress is that implemented by Karp and Anderson to deal with this kind of an issue and with ground clutter breakthrough. So these techniques are ones which need to be developed for all ground-based radars that are looking for relatively small aircraft, and the nose on a Piper Cherokee of 1 meter squared. Now, I haven't the foggiest idea what the cross-section broadside of any of the newer technology low observable aircraft is, but one would make a guess that it's down in this area. And so there are a lot of point targets that have to compete with it. So bird handling the bird false alarm problem is a major issue in any radar that's dealing with targets the size of a Piper Cherokee or smaller. And one method people use is developing area CFAR techniques that would set up layers of false alarms, layers of false alarm techniques that would work one after the other with different time constants in each, and would divide up an area, say 4 miles by 4 miles, and they would say, gee, we've got a lot of very small targets in this area. It's probably bird migration, and what we don't want to do is we don't want to initiate targets on those detections. We'll continue through following targets that are big, much bigger than, but the algorithms that are used are many and varied, is the best way of saying it. And they have to do with the environment of the area that you put the radar in, the bird population, the ground clutter. Say you had an aircraft that was in a valley and there was a, like in Afghanistan, it was in a valley and there were mountains all around it. Even with an elevation angle of a couple of degrees, you're going to have hellish ground clutter. And so all these things need to be taken care of, and the CFAR techniques need to be developed that will adapt to that environment and tend to be multi-layered in the size of how they measure the area, the criteria for initiating tracks or just continuing tracks in an area, and they have a different time constants in updating them. So if a giant flock of birds came through, one area might be desensitized while the flock came through, and then automatically this system would sense that you're not getting false alarms, that you need to do that, and it could slowly move back down. So you can see that the area CFAR techniques can be very sophisticated and an area of great intellectual depth, which is data-driven. Because pretty much all this stuff can be programmed in one PowerPC. But it's the algorithms that you implement that make the real difference. And they need to be tested in the real environments that you're going to work under.